Okay, when we left off, we were talking about insulators and how charges are not allowed to move around freely in an insulator. Polarization can still occur in an insulator, but the charges cannot jump atom to atom like they do in a conductor. Polarization still occurs, but it involves charges moving within atoms, not between. You can think of this as like the electron cloud, a little flashback from chemistry. It gets distorted to one side or another. So like one side of the atom becomes a little more negative, the other side becomes a little more positive. Okay, that's an insulator. It's different from a conductor. So, let's see, where were we? Insulators and conductors. Okay, now we're ready to talk about what actually happens in polarization. I'm going to make some drawings. I'm going to show essentially the step-by-step process of what happens. So let's start off with a neutral object. I'm just going to draw a square. I'll throw four, this is not the marker I was using. We'll throw 4 negative charges in there. And we'll throw 4 positive charges as well. And you're going to notice something, that I'm going to conserve charge in my diagrams. What that means is if I start off a series of diagrams with 8 charges, I better have, unless I'm adding some from some other source, I better have 8 charges at the end. Conservation of charge is a real thing. You cannot create or destroy charge. Okay? So, here's a neutral object. Now, you take this neutral object and you bring in some outside charge, so some other object. So here's what we're going to bring in. We're just going to bring in a rod. That's going to be a negative rod. Okay? So now I'm not conserving charge because I'm introducing a new object. Okay? So our new object has been brought near our original object. And what's going to happen, let's assume this is a conductor, just so it makes it even more clear. Let's assume that this is a conductor. Now, what type of charge is locked in place or can't move? That would be the positives, the protons in other words. These charges will not move in response to the neutral or the negative rod coming in, but we have a bunch of negatives coming in. The negatives in here can move. Are they going to want to go near this or away from it? They're going to want to go away because like charges repel each other. So, sorry, my phone's ringing because Geneseo's calling and they want money. I'm not giving them any money. They got 80,000 of my dollars, not getting any more. So, the negatives, anyway, before I was so rudely interrupted, the negative charges in this conductor are going to go to the corner. Okay? They're going to go down to the corner here. They're going to repel as far away from this as possible. And what this has really done, okay, the charge is now effectively split. How do we know the charge is split? Okay, well, if you look, this lower right-hand corner is where all the negatives are. The rest, kind of the upper left-hand side, is positive. We have taken charge and we have separated it into 2 different areas. Okay? The important thing here is that with polarization, if we just polarize something, there is no transfer of charge. There is no transfer of charge with this. That is the most important thing with polarization. I have not changed the charge of this. This is still neutral, but the charges are split up. And most charging starts with some, or most of the time we're changing the charge of an object, it starts with some sort of polarization. Okay? Something gets polarized. So what I'm going to talk about now is 3 different methods of charging. First one I'm going to do is charging by friction. This is electrons getting transferred by, for lack of a better term, rubbing. 2 objects rubbing against one another. Okay? Let me go get some objects real quick. You guys saw this last year. I'm getting a piece of fur, and I'm getting a rod. Just a stick. Okay? Transferring by friction simply involves two objects sliding past one another, okay? What is happening here is, I think, let's see, I always forget which one's which. What is happening here is the fur typically tends to, I think the fur gains a lot. It depends on what materials you have. But let's just say that both these are neutral to start off. If I rub the stick across the fur, what might happen is some of the electrons in the fur, maybe they're not very tightly held by the fur. So they can tend to kind of leave and go to the stick. Now if the electrons leave the fur and go to the stick, now I have an excess number of negative electrons here in the stick. I have a lack of electrons here. In other words, I have more protons than electrons, meaning this fur would be positive. So whichever way the electrons go, that becomes the negatively charged object. Okay, if we start with two neutral objects, okay? But that should be a little reminder of what we were talking about here. The stick and the fur. So, real quick, couple of pictures. We're going to start off with a neutral stick. It would help if I could spell neutral. Neutral stick. And how are we going to show that it is neutral? We are simply going to put an equal number of positives and negatives on. Plus, minus, plus, minus. And then we have some neutral fur. Okay, they are neutral, both of those. We rub them together. And let's say, for the sake of our example, that the negatives get taken off of the fur and they go to the stick. The positives aren't going to move. We're going to fit some extra negatives in there. We now have a negative stick. What is the charge on this negative stick? Well, there are two more electrons than protons in the stick. And again, we're not, obviously there would be way more than just 2 electrons and 2 protons in the stick, or 4 electrons and 2 protons. But I'm trying to simplify this for a drawing, okay? So, 4 electrons, 2 protons, the net charge of this is -2 elementary charges. The fur, on the other hand, has lost its electrons. It is now positive. +2 E. And this again shows the idea of conservation of charge. Okay? I have not created or destroyed any charge in this problem. In my drawings, I encourage you to do the same. Conservation of charge. Fur loses 2 electrons, and the stick gains 2 electrons. Basic. Easy stuff. Okay. Really basic, really easy. Real quick, before I move on to my example of like how this might get asked in a mathematical sense, let me give you, let me just give you a real quick interactive display of what a conductor and an insulator are. Let's go to the simulation. Let's actually do this. Okay. So on the simulation, we have a couple of metal plates here and here. We can polarize those metal plates with this balloon. Notice that no matter where the balloon goes, its charges are kind of locked in place. Balloon is a good example of an insulator. These metal plates are good examples of conductors. And notice, if I take the balloon away, and of course it's not going to work perfectly because this thing hates me, but look where the charges go. Okay, these are conductors, they're little metal bars. Look where the charges go. They go to the outside. They're trying to spread as far apart as possible. I don't know what these two's deal is. I don't know what this one's doing here. It should be spread out as far as possible. I think there's something wrong with this simulation. Okay, not the physics of it, but the just like its little bug. Okay. All right. Let's go back to methods of charging. I've got one example. We're going to write out. So here's our example. If you have a comb, and that comb picks up 8 times 10 to the 4th electrons as it goes through someone's hair, what are the charges on the hair and comb in coulombs if each started as neutral? So here's another example of charging by friction. Comb drags through hair, you have two objects sliding across one another, so some charge is going to get taken, some charge is going to get added onto a different object. Taken off of one object, added onto another. First thing we need to do is we need to figure out, well, this is how many electrons got moved. How big of a charge is that in coulombs? Very easy to do so. This is just a unit conversion problem. 8 times 10 to the 4th elementary charges, okay? An electron is a negative elementary charge. A proton would be a positive elementary charge. So we have 8 times 10 to the 4th elementary charges. We know from above that one elementary charge is equal to 1.6 times 10 to the negative 19th coulombs. We multiply these two numbers together, we should get 1.28 times 10 to the negative 14 coulombs. Now, some of you, and some of you last year did this, you looked at this and you said, wait a second, you said that this has to be a multiple of 1.6 times 10 to the negative 19th. It is. It doesn't look like it, okay, because the exponent is different. But trust me, this is, what, 80,000 times 1.6 times 10 to the negative 19th? Okay, this is fine. So this is the amount of charge that got transferred. If we want to write the final answer, we would say that the hair now has a charge of positive 1.28 times 10 to the negative 14th coulombs. And the comb, since it gained the electrons, has a negative charge. Gain electrons negative, lose electrons positive. Isn't that Genlep from chemistry? Yeah, I think it is. Okay? Simple, but something you need to know how to do. Let's move on to the second method of charging, charging by conduction. I guess I was just thinking of this because I just got shocked when I was at the board, just a little tiny bit. This is the method of charging that happens when you get shocked by something. Okay, that's charging by conduction. So essentially, here is what we have. This is charges getting transferred by objects that are touching. And these touching objects are usually conductors. Okay, they're objects that conduct electricity well. Insulators, the charges won't jump around as much, obviously. So, here's what we're going to do. Let's take, again, a neutral object. Plus, minus, minus, plus. Okay, and here's what's going to happen. We're going to take this neutral object and we're going to bring a charged object near it. And what's going to happen? Well, we take a neutral object, or any object, we put another charged object near it. That is going to cause polarization first. Okay? So let's take a negative object, and we're going to have it touch, that's much bigger than I meant to draw it, our neutral object, our neutral object. The positives are going to stay in place, but what about those negative charges in the originally neutral object? They're going to want to get away from these negative charges over here. They're going to move that way. Okay? Now, what's going to happen here is these negative charges, they don't really want to be surrounded by a whole bunch of other negative charges. So what's going to happen? They're going to see this neutral object, and a couple of them are going to jump ship. Okay? Some of those neutral charges are going to jump ship. They don't want to be surrounded by all the negative charges. So what actually ends up happening is these charges are going to move over here. We take that originally neutral or charged object away. Now we've got a whole bunch of charges because those negatives, they were kind of packed in there together. They don't want to be packed in there like that. They're going to see this neutral object and think, hey, let's go over there. But a whole bunch of them are going to go over. So now we're going to be left with this. Now we've got an imbalance of charge. Okay? If we take the neutral object away again, it has reduced its charge, but the originally neutral object has gained some charge. We had charges transferred. And these charges transferred from more negative to less negative. Okay, the electrons are trying to go where it is less negative, where there are fewer negative charges. So we ended up with, let's see, this started off as -4, this started off as 0, now we have -2 and -2. That is charging.